hope everybody's doing okay. I put together a couple of slides for reviewing probability. If you want to check this out in your textbook, it's chapters 6, 7, and 8. We're going to do a few slides, and then we're going to go into breakout rooms and do a few problems, and then we're going to do a couple more slides, and then we're going to go back into breakout rooms and do a few more problems, and then we'll do a couple more slides, and then we'll do some problems individually. And I hope to have you out of here by 8 o'clock. That would be the goal. All right, so we're going to start with probability rules. These are the things like in a probability distribution, all of the probabilities have to add to 1. So that's that idea of the sample space in the first bullet. The second one is that all probabilities have to be between 0 and 1. Something can have the probability of 1, which would make it certain, and something could have a probability of 0, which means that it would never happen. But mostly our probabilities are somewhere between 0 and 1. Probability of an outcome occurring equals 1 minus the probability that it doesn't occur. That's the idea of complementary events. And then the probability that 2 mutually exclusive or disjoint events occur is 0, because mutually exclusive events are like in a Venn diagram. Those circles never overlap. So the probability of both of them happening at the same time is going to be 0 because there's no overlap in mutually exclusive events. Any questions there with those basic probability rules? Okay. Strategies for solving probability problems, tree diagrams, Venn diagrams, charts, tables, and also that normal curve helps us find probabilities often too, if we know that the distribution of scores or values or whatever are normal. We can use the normal curve to help us along. All right. Is there a formula on the AP formula sheet that applies? These are the formulas that you will find on your laminated card. This one is saying the probability of A or B is equal to the probability of A plus the probability of B minus the overlap, if there is any overlap. The probability of A given B is equal to the probability of A and B divided by the probability of B, and order really matters here. Wherever that given line is, anything that follows the given line is going to become your denominator. So that's really important. So it's the and of both of these things is in the numerator, and the denominator is just going to be whatever is after the given line. This is talking about expected value, where maybe you have a probability distribution with the x values on the top and the probabilities on the bottom, and you want to know the expected value of something. You multiply the x times the probability for each one of those and then add up the pieces. So that's what this is saying. This has to do with variance. So if you are finding the variance of a similar distribution where you have a probability distribution chart and the x's are on the top and the probabilities are on the bottom, this is how you would find the variance for that. Again, you're using the probabilities, but you would take all of the x values and subtract their means, square them, multiplied by their respective probabilities, and then add them all up, and that would give you variance. And if you wanted the standard deviation, you would just take the square root of all that mess. And then this down here, this is talking about binomial distribution, because we can see that binomial coefficient here. Another way of writing this is NCK, where we're talking about combinations. So all the different ways we could maybe choose 3 out of 10. Something like that would be a binomial coefficient, and then we've got the probability of something happening, and maybe there's 3 of those, so we raise it to the third, and then 1 minus P or Q probability to the n minus K. So if this was 10 and that was 3, then this would be 7 over here. So these are all things that show up on your formula sheet. Of course, we know that there's going to be things that doesn't show up on our formula sheet. So these are some of the things that will not. This idea that if events are disjoint, then the probability of A and B happening is going to be equal to 0. Again, this is just saying what I was saying before, which is disjoint events. Disjoint meaning that they're not touching. So we've got 2 circles in a Venn diagram situation. These things don't have any overlap. So the probability of them happening together at the same time is going to be 0 because they won't ever happen at the same time. They don't touch. They are disjoint. If events are independent, then the probability of A given B is equal to the probability of A times the probability of B over here. And this is another way of saying that, but more commonly we would see this. If the probability of A given B is going to be equal to the probability of A times the probability of B if those events are independent. This is where we're combining random variables. So mu of A plus B is equal to mu of A plus mu of B. That came up recently in class. And then also we can combine variances. Remember that if we're given standard deviations, we're going to have to square them both first, add them together, and then we can take the square root after that. And then you're never going to see a z-score on your formula sheet, but we all know how to find a z-score. So that's another important one that we can use. Questions? All right, then. It's time for us to do some math. We're going to do, in breakout rooms, probability, why is it so hard? And there's about 3 pages there. There are 5 problems, but they're pretty well spread out and they're going to go pretty quickly. So I think we can get that done in 15 minutes or less. Again, that's the front cover. I think Eliza's the only one who doesn't have this. I will try to, let's see. I wish I could just give you this link, but I don't know that.
If you just put it up there for a second, I can take pictures with my phone and just look at those.
Okay, all 3 pages?
Yeah.
You got it. So here's page number 1.
Okay.
And page number 2.
Okay.
And does that get all the way to the bottom? Yep, C is the last thing there. And then page number 3. So, binomial distribution. So we talk about something called the binomial setting. It's got those 4 pieces. I think we talked about these not too long ago also in class. We know that we've got a fixed number of trials. This is the BINS, right? B-I-N-S. So B, there's 2 outcomes, success or fail. It's binary, so that's the B. I is for independence. N is for the fixed number of trials. And then S is that the probability of success is the same each time. So B-I-N-S, BINS, for our binomial distribution. Sometimes we're looking at a situation that isn't geometric, although it starts to feel a little binomial. It turns out that it's geometric because it doesn't have the fixed number of trials. So geometric distribution, the difference between geometric and binomial is that this one doesn't have a fixed number of trials. You're just going to keep on shooting the dart until you get a success, or you're going to keep on shooting the ball until the ball goes in the hoop. Or you're going to, I don't know, keep on doing your homework until you get an A. So much of it is the same. The binomial part, 2 outcomes, yes or no. The independent part, the I for BINS, and we've got the probability of success is the same for each trial. Those things are all the same as binomial, but we don't have that fixed number of trials here. We're just going to keep doing it until success is achieved. So that's binomial and geometric. And then a quick look at normal distribution. We should know that if we have a binomial situation and our sample sizes are so big that n and p and n times 1 minus p are so big that we can apply the normal distribution, then we like to go from binomial to normal. But you could continue on with binomial distribution if that's what you're comfortable with. But you should know that as things get big enough, we can go ahead and say, you know what, this is going to look approximately normal. So if the data is modeled by a continuous distribution and is given as normal, that's one way to do it. And the other way is if it's modeled by a binomial distribution, but NP and n times 1 minus p are large enough, then you can go to a normal distribution. We like the normal distribution because we can use normal CDF and INV-norm, and we can find z-scores. All of those things are familiar to us, and so we like to get sort of into that setting. All right. Sometimes we can solve a problem with simulation, but there are some important things that you have to remember with simulation. Model the component of interest in the problem with some chance mechanism, like rolling a die or on a spinner or using a random digit table. State any assumptions being made, usually independent trials and constant probabilities. Describe how the simulation will run. So you have to actually write out the description. You have to talk about what's going to happen if the same number comes up twice. When are you going to stop? So if you're trying to figure out how many people might get the flu out of 10 people, you're going to have to stop after you get 10 numbers. And if each person is, generally it wouldn't be each person is assigned a number, but rather, you know, these numbers are assigned to the flu and these numbers are assigned to somebody not having the flu. And then you don't have to worry about duplicates, but you do have to worry about duplicates if we're talking about duplicating the same person or the same subject. Conduct the simulation with a reasonable number of replications. So do it like 50 times so that you can build a nice dot plot and get some information out of that. So you might be able to find a p-value in there somewhere, and then state the conclusion reached in the context of the problem. So we've done a lot of simulations in class. I feel like this is going to be pretty good for some of you. And we'll probably do another simulation problem before the 25th of May. So just keep that in mind. We're not doing simulation tonight. All right. So we're going to go back to breakout rooms and do some more. This time, we're working on where it says probability distribution. So we're into page, I don't know, 4 or 5. If you go in a couple of pages, you're going to see probability distribution at the top. And I'm going to find that really quick for my friend Eliza. And this is just one page, Eliza. So it's just this front page right here. So it sounded like those problems were a little bit better than the first ones, or maybe we had talked enough about probability that you felt a little bit more confident doing some more problems. Again, I'm not giving you enough time to do them all. I understand that, so don't feel pressured to answer everything. I will put the solutions up to those as well tomorrow. So we just got a couple more slides and then some multiple choice problems to try. So mutually exclusive versus independence. This is all about mutually exclusive. I think this is the easier one out of the two for sure. Again, mutually exclusive events means that there's no overlap. Another word for mutually exclusive is disjoint, because they are not connected, okay? So these are mutually exclusive, two circles that don't overlap. Non-mutually exclusive would be circles that do overlap. Okay, so to find the probability of A or B here, you'd have to take the probability of A and add it to the probability of B. But over here, if you were looking for the probability of A or B, you can't just add all the A's and all the B's. You're going to have to subtract out this purple part here because it got counted as an A and it got counted as a B. So you're going to have to take that part out. We don't really have a great picture for independence. We do know that it looks a little like this. There is overlap on independence because you can't be independent and mutually exclusive at the same time, because independence implies that there is some overlap. But it doesn't mean that all circles that overlap means that the events are going to be independent. So you have to really dig a little deeper. So one quick way to just figure it out is, and I probably didn't explain a very quick way when Ella asked the question early on. This is probably a better way to have done that problem. So the probability that you're a child, given that you ordered American food, has to equal the probability that you're a child. So that would have been easier than trying the flip-flop of these two. So I should have done a better job with that, and I apologize. So the probability that you eat American food, given that you're a child, is equal to the probability that you eat American food. Or if A is representing child and B is representing American food, then it would be the probability that you're a child, given that you order American food, has to equal the probability that you're a child. This given that part shouldn't count. It shouldn't do anything. If it does do something, then the events aren't independent. They're dependent. Okay? We do know that if events A and B are independent, then the probability of A will equal the probability of A times the probability of B will be equal to the probability of A and B if the events are independent. All right. So independent is the hardest part about probability. And so spend some time on that when it asks questions. Go back to the table, really take a look at that table of the Mexican, Greek, Asian, American food, barbecue, and the children and the adults. And you can, I think you'll be able to see in there. I think it was kind of easy when you looked next to it at the Asian food. You could tell that if you're an adult, you're more likely to order Asian food than you are if you're an American, than if you're a child. So dig into that a little bit. Use this slide as a reference. These slides will be posted for you. And just capture this. If you're going to capture one thing, this has to be true for events to be independent. The probability of something given something else has to be equal to the something when it's not given something else, like without that part. All right. So the only way to do better on the multiple choice section is to continue to do more multiple choice problems. So after you turn the page from probability distribution, it says 5 for 5 probability. There are 5 multiple choice problems. We're going to work on those independently now. And you can shoot me what you think are the answers in the chat. And I would appreciate it if you just sent it to me and not everyone, because then everyone will know what the answers are. So use the chat to just go ahead and direct message me what you think an answer is for a particular problem, and I'll let you know if you're right, or if you want to just try all 5 and shoot me all 5 answers, you can do that too. And then once you've given these 5 problems a try, it is time to get on with the rest of your evening, whatever that looks like for you. So I'm going to stop sharing. Nope, first I'm going to go over here. And for Eliza, there's 2 pages of that. This is the first page, 5 for 5.
Okay, got it.
And this is the second page with the other 2 problems.
Thank you.
You're welcome. All right. So